All right, in Solutions Podcast number 7, I'm going to talk to you about something called colligative properties. And before I get to that definition, I want to give a brief overview and define just some physical properties in general, which can be categorized as either extensive or intensive properties. So an extensive property would be something that was dependent on the size of a sample. Two examples being mass and volume. Intensive properties, on the other hand, are characteristic of that substance. So if I have a 100 milliliters of water, the density of that water is going to be the same regardless of if it's 100 milliliters or 500 milliliters. If I am boiling water at 1 atmosphere of pressure, it will boil at 100 degrees Celsius, regardless of if I'm boiling 1 cup of water or 4 cups of water. All right, so that's an important distinction I want to make before actually moving in and defining a subset of intensive properties known as colligative properties. These are physical changes that result from adding a solute to a solvent, okay? Adding a solute like salt to a solvent like water. They depend on how many solute particles are actually dissolved, all right? But they do not depend on the type of solute particles that are dissolved. Say, it wouldn't matter which type of salt or if it was glucose versus sucrose. That does not matter. The only thing that matters in colligative properties are how many of those solute particles are actually dissolved. So let's look at some examples here. There are 4 colligative properties, and your Georgia Standards of Excellence want you to know about 2 of them. There's an emphasis on boiling point elevation and freezing point depression. And you're going to explore both of those in an inquiry-based lab. However, I have to discuss all 4 of them. I feel it's almost impossible to talk about these without addressing foremost the vapor pressure lowering. So I'm going to go ahead and do that for you now. Both of these highlighted in yellow, I'm going to hit them both at the same time. So there is a reason why there is a boiling point elevation. So let me give you an example. If I want to boil my macaroni in my house, I could add some salt, okay? And that would increase the temperature at which water actually boiled, all right? So that's one example of boiling point elevation, but I want to talk to you about why it occurs. So if you would look at this schematic here, on number 1, we have a volatile solvent. Don't worry about that. It's let's say it's water, okay? And above this water, so we have a phase change here occurring from the liquid to the gaseous state. That's really what these are all about, are these phase changes. So in this diagram here, it's showing gaseous particles and liquid particles, and it's showing particles that are escaping into the gaseous phase and those that are re-entering into the liquid phase. All right. In diagram number 2, however, there are solutes that have been dissolved. Okay, now if you notice, they are disrupting that interface between the liquid and gaseous phases. So, water molecules in this example are unable to escape into the gaseous phase or re-enter into the liquid phase. All right, so what that does is it leads to a shift an equilibrium, something we will get to at the end of this course, but I can still throw out the word. All right, that will lead to a shift. And what you're going to see overall is the vapor pressure here is much lower. Okay, why is the vapor pressure lower? Because less molecules are able to escape into the gaseous state. So that lowers the vapor pressure. Let me tell you something else real quick. Boiling point. Let's get a definition. All right. Boiling point was one of those intensive properties I just mentioned. Okay. And so boiling point is the temperature at which vapor pressure in the liquid equals the external pressure surrounding the liquid. All right. So if we say we are at 1 atmosphere of pressure, for example, these 3 vessels are not moving locations, so consider their external pressures as constant. All right, let's call it 1 atmosphere of pressure. So in scenario 3 here, the vapor pressure has lowered. Now, what does it mean to boil? It means that the vapor pressure equals external. Well, if the solutes have lowered that vapor pressure, then it's going to take more energy input. It's going to take a higher temperature for this solution to boil. Hence the term boiling point elevation. The animation here on the left is showing water molecules, and this is a pure substance. This is a pure water molecule at 1 atmosphere pressure and whatever temp. It really doesn't matter, okay? You know, let's go ahead and just call it 100 degrees Celsius and keep it very simple here. Now, take a look at this. Now we have other solutes that are dissolved within that solvent, okay? And you'll notice that there are less molecules entering. Therefore, there is a lower vapor pressure, which again means in order for this substance to boil, temperature will need to increase. All right, so the next one, freezing point depression. I can relate to this, and most of us can relate to this even in Georgia after some of our winter storms that we've had here recently. Okay, the idea is the same. When a solute is added to a solvent, those interactions prevent the solvent from going into a solid. So now we're talking not liquid to gas, but we're talking liquid to solid. Okay, now I'm going to stay with water. When water freezes, it forms this incredible lattice structure. All right, so when there are solutes that are in with that water, it disrupts the formation of the lattice structure. Okay, in other words, it prevents the water from entering into the solid phase. Okay, so as I said, it's all about these interactions that are occurring. So in order for the liquid water to become solid water and freeze, the temperature must go down. Okay, and this is really cool and has a bunch of applications in the real world, because we have salt trucks. All right, that's why salt is put on the icy roads. That's why salt melts, ostensibly melts the ice, but what it's doing is it's lowering that freezing point, so it stays liquid longer. However you want to conceptualize it, this schematic is showing that same thing here. So this is a simplified, very simplified lattice, okay? And we have it freezing, and here these are, this is liquid water. Well, when we mix these solutes in here, like salt, you can see now we have more water remaining in the liquid phase, okay? And that is known as freezing point depression. These also tie in with vapor pressure, as well as some really cool thermodynamic discussions that we'll have later regarding enthalpy and entropy, okay? I also want to mention, because I just want you to know about it, really. When doing calculations, which we will not do in this course, with colligative properties, chemists use something called molality. Molality. And no, that's not spelled incorrectly. It's not molarity. It's molality. Okay. So, and really what it is it's moles. If you think of molarity, we had, you know, moles per liter. So this is moles per kilogram. Okay, so moles of the solute per kilogram of the solvent. All right. Now, the reason for this is because when we are talking about colligative properties, we are talking about changes. We are talking about changes in temperature. So what changes when temperature changes? Volume. If volume changes, we can't use molarity. Okay, molarity doesn't work. We have to use this term of molality. And I had a student last year come up to me and say, I never heard of this. So I want you to know about it moving forward, whether we're using it in this particular course or not. I still want to teach it to you. Okay, just like I want to talk briefly about osmotic pressure, so that way I feel better because I've gone over all 4 colligative properties, not just the 2. Osmotic pressure, okay, the movement of water, and water is going to move to dilute. You guys are probably experts on this after biology, all right, and that's all this is. If we have this system here on the left at its initial state, and then it moves into equilibrium with all the glucose being the solute, which will change the properties. These are the colligative properties. And not only will water then flow, notice how water level has gone here because water has moved to dilute. But look at what happens also to the osmotic pressure. There is a change there as well. So the more solutes that you dump into the right side, the more the water will move through and diffuse across a membrane. Okay, so that's what colligative properties are all about. There's no problem set for this podcast. We will do this in lab, and I'm even thinking that we might even make some ice cream. All right, guys, I'll see you in class.